Hello, everyone. Welcome, and thank you for taking your time to join us today for the webinar Space Avionics Design Nuggets. I'm Abhirami Mahira, Team Lead for Business Development with AADYAH. For the benefit of those joining us for the first time, let me take a minute to share a brief on what we do in AADYAH. As a global space technology company based out of India and the US, we develop critical systems for launch vehicles, satellites, and space situational awareness. With multidisciplinary teams mentored by space industry veterans, we are development partners delivering turnkey solutions in motion control, computer vision, communication, and avionics. Today, it's our pleasure to host a discussion on the design considerations for space avionics with Mr. Sethurajan Shanmugam. A word about our speaker. Mr. Sethurajan is the General Manager for Embedded Systems at AADYAH, guiding the teams on the development of avionics and embedded systems and flight software for launch vehicles and satellite programs. Along with AADYAH, he is closely associated with multiple programs like Moon Lander Mission and Inter-Country Satellite Mission. He had been associated with Honeywell India for almost 15 years, during which he provided engineering and business leadership in multiple aircraft systems, including environmental controls, cabin pressure control, flight management system, and surveillance system. He had also worked with power and industrial electronic controls manufactured in India under collaboration with global majors such as GE and ABB. We are very delighted to host you for the session, sir. Before we start, a few guidelines for our audience. We'll be conducting a Q&A at the end of the session. If you have any questions during the webinar, please type them into the Q&A window you can find towards the lower end of your screen. We shall be addressing them during the Q&A. When a query is being addressed, I shall unmute the speaker for a better interaction. Over to you, Mr. Sethu, to lead the show.
Thanks, Brahmi, and that was for the nice introduction. And then welcome the hearty welcome to all participants. We have an exciting evening ahead. We have put together exciting back, and space is always exciting. So discussion on space will also be exciting. So without wasting further time, let us deep dive into the presentation. Okay, so the way we have organized the package for you today, this evening, is that we will give you what we define as a space avionics. We also give you an idea of what the space avionics role in a typical spacecraft or satellite is, and we also give you the list down all the challenges what the avionics faces in its operation. Then we deep dive into the design and then address each one of these challenges, and then we also will provide you some of the design nuggets based on our experience with the phase avionics as such. So the first and foremost is what do you mean by phase avionics? The phase avionics, in a very, very generic term, encompasses all the electronic subsystems which go on board the spacecraft or a satellite. It may be a lunar vehicle or it can be a Mars lander, but it encompasses all the electronic subsystems, components, instruments, and the functional elements which are included in the spacecraft platform. Now, what are these components or the subsystems wise? So the primary ones, which are the first and foremost, is what you call as a command and data handling. It may be a little bit unfamiliar to the participants other than space. What is here we are referring to as system is that which receives the command from the ground center, and then it executes those commands. And then the system also handles the data traffic between the satellite or the spacecraft and the ground. So that's very much the very major subsystem on board the spacecraft. Obviously, the software is another major component of the spacecraft subsystems. Then apart from the software, we have the other major systems such as the power, thermal, and of course, each mission will have a dedicated payload and the subsystems avionics. So there is a portion of the space avionics which is also dedicated to the payload of subsystems and avionics. So that's in short, it's referred as a PSA. So the command and data handling and the flight software, or we can consider it as a subdomain. Over the graphic here, we have chosen the what we call as a lunar atmosphere dust and environment explorer aircraft, which NASA has sent in 2004, and as per plan, it impacted the moon. This I choose it because it has got all these major subsystems like the command and data handling captured, the thermal, as well as the. What you find depicted in the graphic is something which is not listed in my text, is the guidance and navigation and control, which is GNC for short. That again is a very, very critical component, and any malfunction, the spacecraft will not reach its intended target. So with this overview, let us jump into the second portion of our package for this evening. Why the space avionics is different from the ground-based avionics or even the aerospace avionics. First and foremost is that the space is not as peaceful and serene as we see it from the ground. It has a very, very harsh environment for the avionics. The space avionics has to encounter what, thankfully, the nature shields us from on the earth, the harsh environment. To start with, one of the first thing is that the radiation. The radiation come from the solar or from it may be the cosmic rays as such, but yet the radiation what the space avionics has to encounter during its operation is the first and foremost challenges it needs to handle it. The second challenge is the vacuum itself. So a vacuum brings its own complexity into the functioning of the normal electronics. So we will deal with detail in the subsequent slides. So to summarize, radiation, vacuum, and then the impact of radiation, like what, the single event upset, what happens inside the electronics, as well as the other factor is the extreme temperature variations, which we encounter in the space, which is almost like 5 or 10x times what we see on the ground, on the earth. And then you also need to consider some sort of sporadic events like a solar storms, but you could have seen how the devastating effect it can have on the spacecraft because they are almost like 40 SpaceX communication satellites were knocked off their orbit because there was a solar storm. Okay, so this gives you a peek of what the avionics has to encounter in space. Now, further on to this one, what are the design criticalities which any phase avionics developer has to address? First and foremost is something which we take for granted for the ground-based avionics. That's the power. All the designer has to keep in mind all the time is that power is a very, very hard commodity to come by, and we need to plan for every milliwatt of power consumption by the space avionics. The second consideration, which has to be at the back of every phase avionics developer, is the mass. A simple mathematics you can say is that every kg addition of mass in a phase mission means that you are going to lose around $1 million, either in terms of additional mission cost or the opportunity cost which you get out of carrying the additional payloads. thermal design is much more complex than the ground-based avionics or even the aerospace avionics, because it doesn't end up in cooling the avionics within their operating range, but it also needs to provide for the exactly the opposite. It needs to heat up the avionics to keep it within the operation range. For example, during a lunar night, the lunar mission avionics has to be kept in its operating temperature range. Now, it is not that you can design an efficient thermal system standalone, because the moment you design a very super efficient thermal design system, you will blow up your mass budget for the space mission, or you will also end up in blowing up the power budget. So it's always a trade-off between your thermal design and the mass budget as well as the power consumption on board the mission. And then consider that the software error cannot be just dealt with by a reset of your computers. It has its own implications on board, although a reset can still happen. But the correcting a software error is going to take you for days or months also, because the entire new software has to be uplinked from the ground, and then it needs to be downloaded onto the avionics. And then, not that it has not happened, but you know how much of impact it will have on the mission, a simple computation error. An example recent is that the Boeing Starliner, there was a software error in initializing the onboard clock, and that had a devastating effect that a Starliner was just meant to dock with ISS never docked with ISS, and the mission has to be abandoned and then had to be landed back to Earth. So a simple initiation clock error can have a devastating impact on your mission. Then comes, which is again a very specific requirement which the avionics has to meet, is the vibration level. They are much greater than what is specified for the ground-based electronic system or aerospace. We are typically talking about 13G levels as well as 20G levels. And the last and foremost is that, which is like repair. You can only repair of any mission avionics. This has to be the only action you can do is to power cycle it and hope that it's able to come back in a healthy state. Now you have here a chart which depicts it from a different perspective, the functional grouping. That means based on the functional features of the space mission. So there again, you have the command and data handling, the electric power systems, the guidance and navigation, and the thermal control systems, propulsion interface. Now let me spend some time on the propulsion interface, which I have listed down for the first time in this presentation. The propulsion interface and control avionics is the link between the onboard computers and the propulsion system, consisting of the thrusters or the reaction control systems, which makes the maneuvering the spacecraft or the satellite in space. So it has a unique function that it has to be the single point interface between the avionics, and although it is also part of the avionics, but also it is the one which is going to command and the propulsion system and get their feedback. Incidentally, I should mention that AADYAH is currently executing a program for a Singapore-based customer exactly for this propulsion interface and control system, apart from the other aerospace program, which Abhiravi mentioned. I will also specifically mention the other piece of avionics, which is, I call it as a changeover control between the main and redundant computer buses or the sensors on board the phase avionics. Now, you may wonder why this requires a special mention, because sometimes it will become a make or break within a mission success, because you need to execute a successful changeover Either it may be between the main and redundant computers, or it can be between the main and redundant buses, or it can be between a main and redundant sensors. Like, for example, there may be two main IMU, or the initial motion unit, or a secondary or a backup IMU. So one of a failure mode occurs in the primary unit of any of this, then there has to be a successful changeover. The next result, what I have listed over that is the one which almost affects what is this effective changeover. That means there is a piece of software on board, which we call it as fault detection, isolation, and recovery, or FDIR by the acronym it is commonly known across the phase domain. That is again a very, very critical piece which needs to function all the time, taking care of the failure modes which occur, and then do the isolation and the recovery in time. And some of these recovery actions, please bear in mind that can have to flow from ground also. And some of them need to be taken by the onboard avionics system itself. Okay, now let us fly through the systems we have seen. One, the command and data handling. I have described them in detail, but let me concentrate on what's the design nugget, what we can focus upon in this chart. The use of the aerospace systems is the key for you to have a optimum command and data handling, because when you start designing the command and data handling for your specific mission, sometimes you may end up in poor design or the design. Both are costly as far as the mission success is concerned. Now, over the right-hand side of the chart, you have a simple flow chart depicting the major steps for the design of the command handling system. Obviously, the commands which need to handle comes at the top of the list. And then you also need to take care of the telemetry. Then you need to decide what's the data rate, and then you need to decide how much is the processing requirements. Then you also need to ask them, because the data, so we also need to consider the storage requirements for that. With that, you can zero in upon your command and data handling system itself. Other major subsystem, as I mentioned before, is the electrical power system. Here again, it's a common knowledge that the solar arrays will be the main component or the main power generation of onboard the spacecraft mission. Then you have the battery as a backup. But the control is a little bit sophisticated, because it is not that you can have a rudimentary solar array, all the power, charging the battery as well as supplying the loads. They also need to be, there has to be an efficient point of operation. So that sort of control, we call it as the maximum power point tracking control, which always sees that your solar array as well as the battery charging is kept at this maximum point of operation. And depending on the power requirements for the components of the subsystem on board the aircraft, you need to design an efficient distribution system along with its safety as well as protections incorporated, including the power current or isolation in case of a fault, as well as we also need to take care of some extreme situation when you don't have adequate power generation. We also need to go into what you call as a selective power off of and maintaining only the critical system which are required for the continuity of the phase mission itself. Guidance and navigation system. This is the system which guides, which takes the spacecraft to its final destination. Now, this is a pure, I would say this is a pure art and science, because most of it is again driven by our mathematical computations of the forces what acts upon the spacecraft, and it's quite a bit of elaborate exercise which starts with your mission planning, and then you need to match your maneuvers with your propulsion system capabilities. That's depicted in the chart as delta V. Delta V is that we import delta to the velocity of the spacecraft. So, and other thing is that not all the times this will be affected from the ground. There are some phases of the mission where the guidance and navigation needs to be happening autonomously. A famous example will be when there is a landing phase in a planetary mission or interplanet mission. There's always time criticality associated with any landing, and the delay between the communication between your Earth and the ground will not enable a ground-based GNC to operate. So the spacecraft into what we call as autonomous mode, where the entire software take care is operated autonomously by the spacecraft itself or to ensure a safe landing. And during autonomous mode, we even don't allow any other change of the mode. Even the safe mode of operation, which is valid for the other mission phases, may not be permitted during this autonomous mode of operation. Let us jump into the thermal control system. It is not as simple as you see in a ground-based avionics system. Here, we need to take care of two things. One is we need to isolate the subsystems from either the extreme cold or the extreme hot. So the isolation comes with the top functionality of the thermal control system. Then we need to transport the heat. Either we need to transport it out of the system or we need to transport it into the system to keep it warm. Then comes the radiators, where we need to dissipate the excess heat as such. So this itself is a science, and then there's always a very, very technology intensive system where every now and then there is always a efficient way of encoding. Again, the mass considerations also drives the development. Now, the design nugget is that suppose you are designing your thermal control system for a sun absent or a lunar light operation. The trick is that you leverage the normal heat dissipation of avionics and try to minimize the excess heating required to keep the avionics in its operating within this or above the cold environment temperature and bring it within the operating minimum limit as such. This I talked about before, and then so I will quickly go over it and concentrate on which is the design nugget over here. This system being the link between the computers and the propulsion system, there is an ideal candidate where we can try to bring in some efficiency by having the implementation through an FPGA. Okay. So with that, we can move over to the other portions, the changeover control between the main and redundants. And then we also need to ensure that this changeover takes place on time so that we don't have an impact on the mission, success of the mission as such. This I talked about in design, so let me focus again on the design nugget over here. Now, the first and foremost in the successful fault detection is how do you detect the fault as such? That means you need to detect the fault or the failure scenario in time, and then the further steps like the isolation and recovery can follow. But the detection is a key step in the FDAR, and the initial or traditionally the FDARs used to be based on the built-in test, or it be based on the models of the subsystem running inside the software. Now, of late, there has been a push towards the use of the AI. That means the AI models, which are you pre-programmed or allow them to learn from the nominal and the fault failure data. So you have the model and then the model operates within the onboard software and then makes the efficient direction of the software. This is supposed to be more processing wise, it is supposed to be more efficient than traditional models running or even the bytes and other ones, which also consumes much of your execution time as well. Okay, now coming to the main topic of this evening, which is the design considerations for the phase avionics. First and foremost is to address the first and foremost challenge, which is in any avionic design, the choice of the optimum processor almost ensures that you have ensured good probability for success or the safe operation of the avionics. But for the phase avionics, the environment causes its own challenges with respect to the choice of the processor. Whereas on the ground-based avionics, it will be based on much more avionic characteristic, like what's the processing capacity required, what's the memory capacity required, what's the probably the response of the system, both in temporal as well as the space domain. So all these considerations, which are the traditional ones, which goes into the choice of the processor, is a little bit complicated into the phase because there is another factor coming in, which is the radiation interface environment. Now, your choice of the processor may be from the radiation environment because it is not the you are going to change the processor, but you need to change the type of the processor, whether you want a radiation hardened processor or a processor which is going to tolerate the radiation, or you can go in with other protection for the radiation, a normal processor. So this decision now is shifting to the environment rather than the avionic characteristics. There are some parameters on which you can try to gauge the radiation environment. One major parameter what is used is the total ionization dose to which the avionics will be exposed during the mission. Of course, the mass and the cost is also another key factors in your selection of the processor. Now, again, if you are able to zero in on a processor which has been flown previously, and then that we call it as a space heritage processor, that will give you a good heads up into implementation of the avionics or the development of avionics. There's a bit of caution around there, is that you may have located a space heritage or a technology readiness level 9 processor, but the same, what you need to notice is that a TRL9 processor for a lunar orbital type of mission may not hold the same tier or may not be qualify at the same technology readiness level for a phase for a lunar landing mission, just because the type of mission is different. So we need to be extra careful in selecting your heritage system, and don't go by the generic tag. You need to see whether the TRL line is for a similar mission to yours as such. Now I will, we have further slides where we deal with the choice whether we need to go in for a radiation hardened or a radiation tolerant processor. Now, a little bit about the interfaces, what the processor need to cater to. First and foremost is you do have a Ethernet or you have a space wire type of, which is space twin of the land-based internet. And you have the normal serial interface. It can be RS432 or RS485 or 232 is also used. CAN is gaining coinage in the nano satellite or the smaller spacecraft and cube satellites. A MIL 1553 is also still present in many of the missions just because many of the sensors which have been traditionally, they have this MIL 1553 interface. There is a huge amount of mass as well as the cost you need to pay for providing the MIL 1553 interface into your computer. And the design nuggets wise, first and foremost is that we need to have the redundancy built into the critical interfaces. Providing redundancy with the computers is not going to ensure you that you have effective recovery action in terms of fall. For example, if you decide to go in with one single IMU for your mission, there is enough possibility that the IMU go out of calibration or become their cumulative error drives it out of the out into the invalid range. So if you have a single IMU, then you are down to see whether we can successfully accomplish the mission goals with other sensors you have on the mission, or sometimes it may end up in mission failure, like what happened in case of the bash sheet Israeli lunar lander. They had ran into a problem with the IMU, and then they tried to restart the computers. By the time the recovery action was too slow, and then they crash landed on the moon. The other thing is that for providing redundancy for the sensors, the immediate tendency of any developer is that wherever the sensors can be crash-trapped within the processor, we can do that one. But remember that you are adding to the mass, and sometimes the additional harness required, you may as well put in additional low-cost sensors rather than cross-dropping between the computers. Now comes what the discussion I have promised. What is the design considerations you need to make when you have to decide whether you go in for a radiation hardened component or a radiation tolerant component? First of all, the definition between these two is not very watertight or very clearly defined. There is one definition going by the amount of radiation in terms of the kilorad or the avionics exposed to. And that definition says that anything above any device which can tolerate above 10 kilorad will be considered as a radiation hardened device, and anything below 100 kilorad, which is normally in the range of 50 to 80 kilorad, can be a radiation tolerant. And sometimes definition can be based on the mission type. Any deep space mission, obviously you need to equip yourself with a radiation hardened. The deeper you go into space, more the radiation also increases multiple fold. Now comes this is the interesting portion of the topic today, how radiation is literally able to drive a dagger into your avionics. Now, I have depicted here three such scenarios where the radiation can cause havoc with your avionics. The first and foremost on the topmost is the low damaging, that is just a performance degradation over time. And if your mission is short, you may be able to recover from this radiation impact. What you see on the series of the four charts over there is the radiation coming inside, and then you have the additional charges created within your silica cell. And then even though the primary ray dries off, the incident ray dries off, you have the trapped charges which are present within the silica, and then which degrades the performance of the electronics. So that's the first of the impact you see due to the radiation. And the more severe, or in terms of severity, you can put it in the middle, is what you call as a single event transient or the single event upset. So here again, the incident ray leaves the causes a transient phenomena, like it can be a current surge going out and then causing an outside electronics to flip its stage, or then it can recover back. That's probably a transient type of impact. The other one is that your memory bit can flip from a high to low or low to high. That we also, but then it can also come back. So this again, we term it as a single event upset. At the bottom right, what you have is the much more damaging. Literally, is that it causes the radiation causes the latch of the memory state or the bit state, and then you can only recover from it by power cycling your avionics, which is again has its own implications. Sometimes it may result in a permanent damage to the avionics as well. So this is this scenario quite brings out how the avionics can be literally stabbed by the radiation as such. Now comes the consideration between the radar. So in view of all this, we can't go ahead and then for a radar device, because for the simple fact, you will blow a hole into the mission budget in terms of the cost, because the cost is nothing, will not be less than 100x times the normal industrial grade processors. The radiation tolerant devices are a little bit gentle on your budget. They are around 10x times the normal industrial grade. Now, here, sort of insight why the radar devices are costly, because the redundancy to handle the radiation failures need to be built into the silica cell itself. With that, let me move on to the what are the protections we can have. Now we know that we can have to build the armor around the device by going in for the hardware, red hardened device. But there are some sort of a simple techniques which we can adapt. So in this slide, you can see that the software also can play a very intelligent role in guarding you against the radiation-induced effect. So we have a name for it called as shift pronounced a little bit differently, or with the I and H interchange, which stands for the software implemented hardware fault tolerance. Now, for the right, you see a simple programming techniques from the C++, wherein you can have a class defined for your triple redundancy variable, and then you can, by simple conversion from one class to another, you can bring in the majority routing, and then you can triplication, you can bring it by the conversion the other way around. So, and there are other sophisticated way of handling the same thing within the software. There is something called as the code comparison itself, wherein you can bring in the sort of a protection in software against the radiation-induced faults. There are also the traditionally protections what you build into the software, like the watchdog timer, which are like handling if there is an radiation-induced abnormality reduced in the operation of the software, the watchdog timer will time out and then reset the processor. There are also, as for the permanent, suppose there is a failure induced, and then if there is a monitoring the software for the overrun, that can trigger a protection measure, and then it can sort of avoid the permanent failure happening in the silicon, inside the silicon. The other protections is obviously the cyclic redundant check or the CRC, as well as the for the memory, as well as the communication packets. Is also will give you a protection against the in software against the radiation-induced defects. Now, in this slide, you can see that even we can't discount anything, any device, electronic device is susceptible in the phase environment for the radiation-induced effects. So we can't rely on hope that your mission will not have a radiation impact. So it has to be your safeguard against the radiation failure should happen with on the design or the testing. Also, the radiation induced is also means that whatever amount of testing you do to simulate the radiation in your phase avionic testing will still help you to ensure the mission success. And now the other thing is that redundancy of the critical system is one more step, so it should essentially take it to overcome the radiation-induced effects. Now, with respect to the radiation, what are the design nuggets, or what is the best practices with which you can adapt so that we make our avionics radiation defect proof? First and foremost is that you need to evaluate what is the quantum of exposure your mission will encounter. Thankfully, there are enough tools available courtesy NASA or ESA by which you can do your analysis. Whatever graphics you see on the right-hand side is one of the analysis done at AADYAH for a satellite mission. And you can, depending on the total ionic dose or TID, what you have this analysis throws at you, you can decide whether you need to go in for a radiation hardened component. Now, don't jump into the radiation hardened component because of the cost. We can also rethink your design architecture, whether you can do away with a system which is radiation, has a high radiation capability. Can you substitute it with your generic system, which is already radiation hardened? Can you implement the functionality within that radiation hardened system? An example will probably make this step very clear is that suppose you are having a navigation where dedicated processor, just like usually the lunar landing, there is always a dedicated processor because of the processing speed requirements, as it. Now that higher processing for the landing, whether it can be combined into a radiation hardened the main onboard computer instead of having a separate the processor, the landing navigation processor itself. So these type of design decisions you need to essentially go through because of the higher cost of the radiation hardened component. There's also some of the tricks is very simple, which is again, you can move the radiation susceptible system into the shadow of the radiation hardened system, or you can simply hide it or tuck it away inside your spacecraft in a place where the radiation is expected to be minimum, and we have some protections which are covering up. Like for example, you can always move your radiation susceptible system into the middle deck if you have some top deck, middle deck, or the lower deck of your spacecraft. So the other thing is that the normal action taken whenever you see radiation susceptibility and then your probability of the higher total ionization dose, you tend to put in the higher or a thick radiation shield. But there is a danger in that one also. Some of the materials what you use for the radiation shield are prone for a phenomena called as the secondary radiation. So providing just a thick radiation shield is not a 100% foolproof against the radiation, because that same thick shield may give rise to a secondary radiation directly hitting your shielded avionics. Okay, I think we have got enough of the radiation. Let us move into the other uniqueness of the phase avionics, which is caused by the vacuum environment. We call it in terms of outgassing. This is because of the vacuum conditions. So all the trapped gaseous molecules of the particle will tend to outgas from any device there, let it be plastic or glue used or a grommet used, or it can be or it can be an avionics package having a trapped gaseous molecules, or it can be a connector. It can be. So the moment the avionic goes into a vacuum, this outgassing automatically happens. Now, it is not that these gases can passively escape into the phase. One of the natural after effect of this outgassing is that you will get your sensitive optical components, such as the camera lenses, will be clouded by this, and sometimes it can be as severe as some of the laser lidars which you use for the navigation, the greater navigation on lunar landing. Those ones also will be clouded by your outgases, and then they become or degrade in the performance. So one of the ways is that you need to look for what is the component which is used in the avionics, which is prone to the outgassing risk, and then you need to test it out. And in spacecraft mission, nothing is left to chance. There is the entire spacecraft may go through what you call as the vacuum test, or more precisely what you call as the TVAC, or the thermal cycling combined with vacuum. And it is not uncommon to see entire spacecraft being subject to this vacuum. And the way the test is being judged for a pass or a fail criteria is very simple. How much is the reduction in the mass due to the outgassing, and how much is the quantum of the gas which has come out of the sample at the test. So these two parameters determine the total mass loss should be less than 10%, whereas the condensed volatile condensable material, CVCM, should be less than 0.1%. Unless we meet these two criteria, we can't completely say that we have a foolproof outgassing proof for avionic design. Some of these obvious spoilers for your avionic design in vacuum will be the wet electrolytic capacitance. So it's a strict no-go as far as the phase avionics is concerned. There is another peculiar phenomena which I want to touch up, is that don't think that your risk just goes up with respect to the vacuum level. There is a phenomena which we characterize by what we call as a Propulsion curve, and that is a curve which has the vacuum plotted against the breakdown voltages. And strangely, you have a possibility of a breakdown or the arcing in case of a vacuum condition happening at a voltage as less as 400 volts at around 5 millivolt. So this means that not the higher vacuum levels is going to cause you havoc. It also something as low as around 5 millibar also poses a risk to the avionics, especially if you consider the tracks adjacent in the PCBSS. So suppose you have a MOSFET bridge and then you have the two tracks running, a MOSFET bridge operating at around, say, 115 volts, may have a spike of around 2 to 3 times, and the transients, especially during the switching of the MOSFET, and that can easily cross the limit of 400 volts, and you may have a spark over between the two adjacent tracks if it crosses around 400 volts. So that's again other consideration you need to make it while you design your PCB layout, which are subjected to higher voltage transients. Now comes the traditional risk of any avionics system, whether be it on ground or be it on space, EMI, EMC. Let me quickly jump in because anybody who is dealing with avionics, for them, EMI, EMC will be a fairly very, very familiar risk. Thankfully, the actions which you take with respect to space avionics is no different from what you take on the ground, in the sense that you need to build the EMI, EMC best practices right from the your switching, right from your PCB layout to your layout of the entire avionics, and especially the routing of cables or routing of the tracks. And you also need to special care about the decoupling circuits and also your grounding scheme. So sticking to the basics of addressing the EMI, EMC may still be can help you with respect to the phase avionics. There's nothing different which you need to take as far as the phase avionics is concerned, but you need to stick to the basics. Just an example of how we can see our little bit of oversight can result in our with respect to EMI, EMC. Over the bottom PCB, you can see there are two tracks which are hardly more than 10 mm long. One of them happens to be a decoupling capacitors ground track. Other one is the I2C bus track. Now, just this less than 10 mm parallel run is sufficient for the noise coupling due to EMI to disrupt the operation of the I2C bus track, and then the entire board will not be operating. Just to illustrate the care we need to take with respect to the PCB layout. Also keep in mind, I mean, if you just connect all your grounds to your box chassis, and then the chassis is still floating in the space, you don't have a sort of a luxury of a metallic structure combining everything, because the spacecraft is an amalgamation of different components, and it is not a metallic structure completely imposing. So your grounding efficiency may not be right, and if you end up in an ungrounded box of avionics, it is as good as not having EMI, EMC protection upward, because your entire EMI, EMC protection is built upon having an efficient path for conducting out your noise currents. You can also adapt the methodology, the tricks up to the designer of the avionics, like you can slow down the clock frequency, or you can make the transitions a little bit slower with respect to rise time or the fall time. That will also give you much dividend with respect to controlling the EMI, EMC on your circuits. Now, let me cover the sort of give you an insight into how the flight software or the software running on the phase avionics look like. Normally you have on a larger spacecraft, you have an operating system, you have a middleware, which is there are enough open source available from the NASA. Like the core flight system is one of the commonly used middleware. then you build your application on top of it. And the best practices with the flight software is no different from what you do on a safety critical software on ground. You need to plan your development cycle with sufficient checks and balances. You need to have a strict configuration controls. You need to do code reviews. Documentation is the key for us to have ensured that the software is made as per the requirements and is verified as per requirements. And you also have to have a robust verification. And the smoke test as the software evolves is also a good way to ensure that your final software doesn't have any major bugs. Okay, let me summarize what we have been talking this evening. We have the first and foremost, we looked at why the space is harsh as far as the avionics is concerned, and what are the dangers which are hidden in the space for the avionics. We also considered how the radiation can literally drive a dagger into the avionics. We also talked about what are the best practices to prevent such a damage to the avionics due to the radiation. We also talked about what are the impact the vacuum brings on the avionics. We also talked about the EMI EMC as such for the phase avionics perspective. So what I wanted to leave you with a thought is that except for radiation and the outgassing, the other practices with respect to EMI EMC or the software is again, we need to depend upon the best practices we follow for the ground-based software or the hardware, and then we need to take the special precautions with respect to radiation and the vacuum. So with that, I will hand it back to Abhirami. You have a thanks, everyone.
Thank you, Mr. Sethu. I'm sure that was quite an insightful session for our audience. Now we move on to the Q&A. Please feel free to drop your questions in our Q&A box. We have a few already in here. Let me start with the one from Mr. Anish. So what he asked is, if the temperature difference is substantially large between the sun side and the dark side on a satellite, can thermoelectric generators be used for generating power within the thermal management systems? So Anish, we are unmuting you so that you can have a direct interaction with him. Please introduce yourself and please go ahead.
Hello.
Yes, Anish.
Yeah, I'm audible.
Yes.
Yeah, hi. Yeah, very interesting session. Got to learn a lot about space avionics. So yeah, I had done a project back in college where we had used thermoelectric generators. So I just wanted to know if the heat difference between the dark side and the sun side is so large, why can't it be used on space satellites as well?
Oh yeah, I mean there are some the thermoelectric generators, we call it as such. There are some of those ones that have been used, but not as a primary power source, but because the other than the solar, the only other primary source which has been used in the space missions is the radioactive isotope thermal generators.
Yeah.
So RTGs we call it. The thermoelectric effect has been experimented and then, but not a very, very stable usage with respect to space missions. I do agree with you that the difference in temperature is large, but again, tapping it and then building an efficient thermoelectric generator and not blowing your mass budget. See, most of the things what you find, even the other energy sources, like for example, the fuel cell or any other source which are there, they are all very attractive as far as consideration for alternative source of the power. But what finally decides whether they are going to be used in a space mission is how are we going to meet the mass budget as such. So it is a trade-off between the mass of your alternative power source system against the conventional one.
Yeah.
Okay.
Yeah. So thank you so much for answering my question. I just had another quick question.
Yeah,
Like
please
you
go ahead.
mentioned, the shielding the satellite from the radiation. Uh, I've also heard that Kevlar is quite effective in blocking out the radiation. Is it still used, or has it been used before?
Come again, Nish. I didn't
Yeah,
hear you properly.
I just wanted to know if Kevlar is being used to protect satellites against the space radiation.
Uh, yes, I think all the radiation sealed materials have been used, and there are new materials also been researched upon. As I was mentioning during my topics, the main criteria is that are you going to have a optimum mass for the shield which you are putting,
Yeah,
and are you free from the secondary radiation aspect? So there is a whole gamut of the shielding which has been used, but the key consideration for selecting your shielding material will be uh, the mass as well as how effective they are with respect to providing the shield. And most importantly, should not generate any secondary radiation.
yeah.
Okay.
Well, thank you again for answering my questions. I think it has cleared all my doubts.
Thank you.
Thank you, Anish. Yes, that was great. I hope that helped you so well. Okay, so we have another question, which is from an anonymous attendee, actually. So, what the person asks is, in your experience, what factor is most overlooked in the development of avionics systems that comes up in the testing phase?
Okay, that is one more interesting question. Thanks for it. And the, uh, the two things. One is that the outgassing is something which tend to be always be overlooked, and then once you end up in yeah, during your thermal vac test, once you are having a outgassing phenomena noticed, that is something which unique to the phase avionics, and not many designers tend to look at it in that way. It is just that because the outgassing phenomena is so complex, sometimes it may be the ingredients which goes into making a component. So that is something which I feel is most overlooked as far as the development of the phase avionics.
Oh, I'm sorry, I was on mute. All right, so I hope that helped. So we have another question from Mr. Shubham. What kind of processor you will suggest for space-based solar power satellite based on microwave technology? Um, I think Shubham
Okay.
left.
Okay.
Okay, yeah, please, sir.
Yeah, I think the process selection is a very I'll say is a exercise which needs to be carefully done. I'll not suggest anything, but as we find in the deck, the most of the process selections, whether you go in for cards or any other custom design or the specific processor, depends upon the size of your spacecraft. For example, for a CubeSat, there is at least to my knowledge, there are around nearly 100 type of flight proven cards processor solutions available. So it's a question of matching your uh, the available processor to your mission requirements. So the straight answer will be that depending on the size of the mission and the task which the processor need to cater, you need to go in for the right sized processor.
Okay. So next we have another question from Eshit. Does shedding materials and the type of orbit have any relationship? And what about off-the-shelf subsystems as well? Let's check if Eshit is online still so that we can unmute him. Yes. Eshit, are you there?
Yes.
Please go ahead and have an introduction.
Okay. Thank you for nice presentation.
Okay. Thank you.
Okay. My question is regarding the shielding materials, and the second is about off-the-shelf subsystems of satellite. The first is maybe, as we know, we have there are so many types of orbits, just
Okay.
like low orbit and higher orbits or geosynchronous orbits, something. Does the shielding materials have their own property depending on those orbits? The first question is this one. And the second is about off-the-shelf materials. Just recently, most of small satellites are already designed and most of them are off-the-shelf materials. So is that any requirements to use this off-the-shelf materials depending on their orbits?
Absolutely. I think there is orbit as a huge criticality with respect to the amount of radiation what the mission encounters. Obviously, a low Earth orbit will be a little bit lesser than, for example, the geosynchronous orbit at a higher point, etc. So your initial radiation evaluation will clearly tell you how much is the total ionization dose expected during the mission and during the orbit, periodicity of the orbit. And based on that, you need to see whether your electronics can withstand that. If it doesn't withstand, suppose you have chosen your car's electronics, then the choice before you is that whether you can build in the additional shielding material so that you can provide the protection. Now, as I was mentioning to the previous question, the choice of cards for CubeSat or NanoSat is pretty much wide varieties of the wide numbers of card solutions available. But you need to carefully study how much is the radiation tolerance they have, and whether it is less than the or whether it is whether it adequately takes care of the total ionization dose, what this your radiation study points out. So what my immediate suggestion for you is that probably evaluation of the total ionization dose for the specific orbit, and then followed by a good look at what the radiation which your card solution can withstand. So with these two critical steps, you may be able to decide upon what needs to be corrective actions for your ensuring that the radiation doesn't affect the mission. Does it answer your question?
Of course, yes. Thank you.
Thank you.
Thank you, Eshit.
Okay, thank you.
We have another question from Mr. Jain. He asks, what are coatings or finishes, avionics related devices that are outgassing resilient, as well as having low magnetic susceptibility for space applications? We would like to unmute Jain so that he can have a direct interaction with you.
Sure.
Looks like he has left. Not an issue. Please go ahead, Mr. Sethu. Do you want me to repeat the question again?
Yeah, probably I must have missed some portion.
All right. What are coatings or finishes, avionics related devices that are outgassing resilient, as well as having low magnetic susceptibility for space applications?
So there are two portions of this question. Is that one is that he seems to require what are the low outgassing material, and the other portion is that he wants probably the same material to provide low magnetic susceptibility. We need to. I'm making an assumption here. He's referring to the EMI protection, I think. So to my knowledge, I don't think there is a material which can provide you both disadvantages of outgassing as well as the low magnetic things. Probably we can get back to him if we have his if we come across. Okay.
Yeah, definitely. We'll try to get back to him on that. So one last question, again from our own anonymous attendee. Is satellite affected with magnetic field distribution by planets? How does it protect?
Okay, the once the satellite affected by the magnetic, is that magnetic variation of the planet or the pull of the, or does it, probably the question here refers to the gravity, I think, if I'm right. I don't know whether gravity, magnetic has been used alternatively for the gravitational pull of the planets. Now, yes, they do have a impact on your orbit. There are some well-known theory how an orbit can be altered in case of a magnetic or the gravitational pull variations, or it can be altered by a slight disturbance in the some of the outer solar system elements as such. So there is definitely an impact, but thankfully all of them are well researched upon, and you have the what action need to be taken, and that's where I think the orbital corrections for satellite comes in, because the moment there are some deviations noticed, a significant one which will impact the functioning or the mission of the satellite, and the orbital maneuvers are done to keep the satellite within the designated orbit. So magnetic variations, field variations, or for that matter, your solar storms, or they also any amount of that. That's why a new topic is emerging, which is called as a space weather, wherein there is enough signs that need to be created so that your mission doesn't get impacted to this weather or space weather elements as such. Okay.
I hope that helps. All right, so we have the final question. This is from Amir Sheikh, and he asks, what is the scope for mechanical engineers in this?
Oh, I think this is, I think probably my one-word answer is the scope of the mechanical engineer in terms of space avionics. I think the mechanical engineers are the ones who design the what I call is the support system for an efficient avionics or the electronic design to function, including the shielding of the avion, or including the entire controller, or what you call as a box design, or even the so mechanical engineers role in space avionics. You cannot. I mean, there's a huge role for the mechanical engineer in electronics as such, because they go hand in hand. The electronic designer and the mechanical engineer go hand in hand for doing a successful space avionics.
Great. I hope that helped him as well. So that was wonderful. Thank you for that warm interaction. We greatly appreciate your time and interest to join us today. If you would like to have more such sessions or any technical support from our end, feel free to write us at sales@aadhya.com, and it shall be our pleasure to assist you. We will be sharing the YouTube link of this session shortly. Do follow our company channel for the updates. So time to call it a day. Thank you once again, ladies and gentlemen. This is Abhirami Mahira on behalf of AADYAH Aerospace signing off until next time. Bye.
Thanks from me as well. Thanks, Abhira.
Yes.